Speeding at sea, it's me, Z. Today I'll be explaining space-time diagrams, which will help us visualize the concepts of space and time and relativity. Whether you're a student, an enthusiast, or just curious, this video is for you. This will also be super helpful for my next video, which many of you were excited about, on how time and space swap in a black hole. There will be some timestamps below, so feel free to click through. Let's get started. Let's start with the basics. In classical mechanics, we often think of space and time as separate properties. However, in relativity, space and time are interwoven into a single four-dimensional space-time: x, y, z, and time. A space-time diagram is a graphical representation of these four dimensions. On a typical space-time diagram, we usually have the horizontal axis representing space, labeled as x, the vertical axis representing time, labeled as t. This setup allows us to visualize how objects move through space over time. For instance, let's say we have an object at rest in space. As time progresses, the object remains in the same position, so we can visualize that as a vertical line. The object is constant in position over time. This line is called a world line. It shows the path that an object takes through space-time. If an object moves, its world line will be tilted. For instance, here's an object that's moving to the right. As time progresses, the object moves this way to the right. The slope of the world line then indicates the object's velocity, position over time. What about an object that moves at the speed of light? We can label the axes in a special unit called light nanoseconds, which describes the distance that light travels in 1 nanosecond. These are great units for human-sized scenarios, such as a person walking or an object a few meters away. A helpful tip is that 0.3 meters, or 1 foot, is about 1 light nanosecond. So here we have 5 light nanoseconds on the position axis and 5 light nanoseconds on the time axis. I labeled this as CT to make the axes dimensionally the same. If an object moves at the speed of light, then it travels x light nanoseconds in position over x light nanoseconds in time, giving a slope 1 line here. Okay, now that you have all the basics down, let's look at some funky examples. What if the light moves to the left, starting at time CT is equal to -5 light nanoseconds? In that case, we start on the time axis at -5 light nanoseconds. Then we draw the object moving at light speed, slope 1 over to the left. The object moves 5 light nanoseconds in position over 5 light nanoseconds in time. If we're moving faster than the speed of light, we can also draw a world line. If we have an object that is traveling at 2 times the speed of light, it will travel 2 light nanoseconds in position over 1 light nanosecond in time. The slope of its world line is now less than the speed of light line. Now we can use the space-time diagram to explore other interesting consequences of relativity. Here's an example scenario. Let's say that we have 2 observers, Ada, who is stationary, and Bob, who is moving at a constant relativistic velocity 3/5 of the speed of light. With respect to Ada's frame, her space-time diagram is simply these axes that we have drawn. But what about Bob? We can actually draw his frame onto this diagram as well. Since Bob is moving at 3/5 of the speed of light, he travels 3 light nanoseconds in position over 5 light nanoseconds in time. Therefore, we can draw the primed t-axis, representing his time with this slope. This axis connects all the events at Bob's position, x prime is equal to 0. For his primed x-axis, we can draw it based off of where his primed t-axis is. We know that for a coordinate system, the x-axis emerges at t equals 0. Similarly, we can start the x prime axis at t prime equals 0 for Bob. We also know that the slope of the x-axis must be the inverse of the t-axis slope, so it would have slope 5/3. Now if we draw this, we can see that for Bob's reference frame, the x-axis has tipped up to form the x-prime axis, and the t-axis has tipped down to form the t-prime axis. Here's also something fun to consider. What happens when Bob approaches the speed of light? Then the x-prime axis and the t-prime axis would both tip towards that dashed line, representing the speed of light. The axes would be the same. In a space-time diagram, the tick marks on the CT prime axis, so when time is equal to 1, 2, 3 light nanoseconds, occurs are located at different positions compared to the unprimed CT axis for the stationary frame. To draw these, we need to introduce the Lorentz factor, or gamma. The Lorentz factor is given by this equation. Gamma is equal to 1 over square root of 1 minus vc squared. This is really important because it will pop up many more times in relativity. For each unit of time in the moving frame, so t prime, the corresponding time in the stationary frame is given by t prime is equal to gamma t. If you're curious about how the Lorentz factor is derived, you can search light clock online for mathematical proof, or let me know in the comments and I might make a video on it. Next up, we can label our axes for Bob's tilted axes. Bob moves at 3/5 of the speed of light. So when we solve for gamma, we get square root of 1 minus 9 over 25 on the bottom, which becomes square root of 16 over 25, and then 4/5. We take the reciprocal to then get 5/4. So for instance, the tick mark for CT prime equals 1 would be located at CT equals 5/4 on the unprimed axes. And we can keep spacing them out like this. For the x prime axis, we have the same, so we can space them out like here. The Lorentz factor is what helps us transform between two reference frames. In our case, Ada, who is stationary, and Bob, who is moving, relative to Ada, which affects both space and time measurements. It not only allows us to transform coordinates from one frame to another, but it also ensures that the speed of light remains constant in all inertial frames, which is a cornerstone of special relativity. Let's put these axes to use to explore a fascinating consequence of relativity. Again, we can keep our two observers, Ada, who is stationary, and Bob, who is moving at speed 3/5 of the speed of light relative to Ada. Let's say that Bob's holding a stick, so he and the stick are moving at 3/5 c with respect to Ada. We can say that the stick is 3 light nanoseconds, or 3 feet long, just for simplicity. Now that we have our axes labeled, we can now define the endpoints of the ruler as A and B. So along the x prime axes, we would have the front of the meter stick at the origin at A, and then roughly 3 light nanoseconds, we would have the point B. Now Bob is holding the stick, so he would see it as 3 light nanoseconds long from his reference frame. What would Ada see? Bob's space-time axes are tilted on the space-time diagram, and this tilt results in a different measurement of the stick's length when Ada sees it. To find the length that Ada sees, we have to move parallel to the primed time axis. This means that we are finding where B, the end of the stick, is in Ada's reference frame. We have to move parallel to the prime time axis because that allows us to transform the coordinates while staying constant in position with respect to Bob's reference frame. The end of the stick is at B, which is constant on the primed x-axis here. So now we're just determining where it is in Ada's reference frame by transforming its coordinates. So let's move parallel to the CT prime axis like this, keeping the end of the stick constant with respect to Bob's frame. Now, here's the punchline. If we look at Ada's frame, the unprimed position and time axes, and draw B here, Ada sees the stick to be shorter. This is called length contraction, and it tells us that the faster an object moves relative to an observer, the more it appears contracted. At speeds close to the speed of light, this contraction becomes more profound. So this example above represented two simultaneous events, the two ends of the stick, A and B. These events appear to be simultaneous for Bob's reference frame, where the stick is at rest relative to him. But for Ada, who is seeing Bob move relative to her, the stick appears shorter. In relativity, simultaneity is relative, leading to the length contraction that we saw here. And we were able to see all of this on a space-time diagram plot. Now that we have that down, it's simple to also translate this result for two events that occur one after another in time. Let's say that Ada is now holding a clock that ticks once every 2 light nanoseconds. We can mark one clock tick as C at the origin, time equals 0 in Bob's frame, and the second clock tick 2 light nanoseconds later at t equals 2 light nanoseconds in Ada's frame, along the unprimed time axis. Ada would say that she sees the clock tick every 2 light nanoseconds. Bob is traveling at 3/5 of the speed of light. So how often would he see the clock ticking in his frame of reference? Now we can draw the clock ticks onto the primed axes representing Bob's reference frame. We do this by drawing parallel to the x prime axis. If we measure where the second tick is on Bob's time axis, it actually happens after longer than 2 light nanoseconds. This is time dilation, which tells us that an observer who is in relative motion with respect to the clock sees it slowing down. The clock appears to tick every 2 light nanoseconds for Ada and longer than 2 light nanoseconds for Bob. From this, we can even say that Bob experiences time more slowly than Ada. Time dilation and length contraction are a direct consequence of special relativity and the nature of spacetime. Accounting for relativity is also crucial for applications such as operating particle accelerators, or even making sure that GPS satellites can provide precise positioning data for our navigational use. Another interesting example is observing muons produced by cosmic rays. Muons are particles that have short lifetimes, about 2.2 microseconds when at rest. From this, you might think that no muons could reach the Earth's surface from the upper atmosphere. But somehow, 1 million of them pass through your body over a single night. The reason that they can travel so far, despite their short lifetime, is because of time dilation. Muons move near the speed of light, so with special relativity, they can travel further before decaying as their lifetime is lengthened with respect to us. And to interpret these remarkable effects of special relativity, space-time diagrams have us covered as our powerful tools to explore the universe. Whether you're a student or were just curious, I hope that this video was informative. Relativity is super duper cool. Thanks for joining me on this journey through space-time, and I'm so excited to make more videos like these. Keep your eyes out for my upcoming video on how time and space swap/don't really swap in a black hole. It's a really cool thought experiment that we can explore with our knowledge of space-time. Comment down below if you have any ideas for future videos or any feedback. And don't forget to follow me on X, formerly known as Twitter, or on YouTube for more physics, astro, aerospace news, nerd content from your favorite physics VTuber. See you next time, signing out.